Hello everyone. Uh, Today I like to explore a bit of how PCI Express works. It could be there's a lot of literature and could be a bit intimidating. It's a complex interface and very powerful. We can transfer gigabytes per second on it. And I think a good way to start in a less intimidating way is to use one of those adapters that we can easily find today. They're pretty cheap, and they come from the time where, well, I guess it still is. It's popular to use GPUs for crypto mining. So those adapters, their mission is to extract one lane from the PCI interface and bring it to this slot over here. This slot is designed to host a classic GPU board, so that's why the interface is 60 lanes in length, but this is a bit of it's just a bit of a mechanical adapter in this case, because through this cable we are going to get only one lane. So in an aspect, this is kind of the most simple interface to a PCI Express you can get. One lane obviously is the minimum. There are ways to get 2 lanes, 4 lanes, up to 16 lanes. But what I like about this method is that in a very inexpensive way, you can plug it to a PC motherboard, to any of your PCI Express slots, and get one lane all the way to here, to your GPU or any other type of card you have. In a very, let's say, minimalistic way. Here, just using, we don't need to read much about it, but just using common sense, in this interface, we should find the minimum amount of signals that PCI Express needs to operate. So yeah, let's try to learn a bit more about PCI Express with those little thingies, and let's give them a closer look. So here we have a couple of pictures for each of the sides of the connector that goes into the PC, just to get our bearings. This is the connector. This is what PCI standard refers as side A, which is the side or the soldering, and this is the side B, side of the components, and just how it compares to a complete PCI card. A disclaimer that I think it has to be said. When you buy one of those adapters, you will see that a number of components in this adapter looks like USB, but it's not USB. If you use one of these adapters, don't use the cable for any other purpose. Don't plug this to any USB device, because what the builders of those adapters have done is to reuse existing USB technology, I guess, to lower cost and make their life easier. But so it's like repurposing USB components for this, to bring PCI Express signals out of a PC. But yeah, this is not a USB device. I'll map each of those connections later, but I just want to mention that with a quick visual inspection, we begin to see some kind of structure, some kind of logic here with those traces going from the PCI connector to the USB connector. We can see that there are clearly three groups of signals. Those signals are composed of two traces that go together from the connector from the PCI connector to the USB connector, and we can see two of them on this side. They end close together in the USB connector. We can see another one here close together to the USB connector, and on the other side is in side B is more difficult to see because we have this the connector itself, the mechanical part in front of us, but it's kind of fair to assume that they have a similar structure, and they probably end up on those two wires of the connector that we don't see here, probably soldered on the other side. I'm going to map all of this, all of those signals, but it's just, I wanted to mention that just a visual inspection gives us some information, and especially everything ties pretty well together if we compare what we see here with the USB 3.0 standard. When we go to the standard, we can see that there are also three groups of signal that they are put together through two wires, through two traces, and we can see the legacy USB standard has those two wires here for signal, and the new, we can call the new USB 3.0 connections through two pairs. And so this begins to, make sense. What's the purpose of reusing existing USB 3.0 components? Because if what you want to get out of a PCI connector is basically three pairs of signals, three signals made of two wires, so USB 3.0 aligns pretty well. So let's map this and let's talk with more information. Okay, so we have more information now. We know where everything goes, and the first type of signal that caught my attention is two signals that they don't even leave the connector, or they don't leave the PCI card, and they are kind of easy to spot because they, as we can see here, they're the ones with a shorter copper. We can see here in the connector, we can see this one is shorter here, this one is shorter here, and those signals, they basically go from one side to the connector to the other side and to this other connector, this other pin of the connector. So basically, this is like an arc, like a short circuit that goes from one pin to another. This is going to basically short circuit a couple of pins in the PCI connector. So I mean, they play a role, and not a big role in sending information. That's the part that we care about. But I think it's it's interesting. It's interesting piece of information that when how PCI Express is designed, and when we plug our connector into the computer board, to the motherboard, and those two pins are going to electrically, they're going to indicate to the motherboard how long is the card we just have inserted. And we can see this better maybe in other cards. For instance, in this one, let me see if I can see them. So as you can see here, we have the same shorter copper that we have in our USB, well, our single lane adapter, and here we have another one. So the way it works is the first pin is common. The first pin in the connector is that helps to measure how many lanes the card has is common. And the second one is going to indicate to the connector that this is a 1 lane card. And the third one is going to indicate that this is a 4 lanes card. So the way it works is when we plug it into our motherboard, the first copper is going to go all the way around. It's going to short circuit the correspondent pin on the other side, and the board is going to recognize that this is a 4 lane card. And the reason why, well, we can see this, I guess, in other boards. Not in this case. Never mind. And the reason those pins are shorter is that for part of the standard of PCI Express is to support hot plug. In some scenarios, especially in industrial PCs, you have the option to insert PCI components when the computer has been powered on. So this mechanism not only tells the motherboard how many lanes, how long is this card, it also, thanks to being shorter, when that short circuit completeness tells the motherboard that the board has been fully inserted. I think it's an interesting piece of information. Not all the cards. You'll see some modern GPUs. They don't have. We can see this pin is shorter. The first one is shorter, but not the other ones. Maybe because, yeah. Now that I'm talking about it, yeah, we are discovering things together. The one that is shorter is the last one. So it's like the only thing this GPU cares about is to indicate that it's been connected in a 16-lane socket, and because, well, obviously they are designed to be running in 16-lane sockets. But an interesting note, and we can play with this. We can play with this another day. The PCI Express standard allows for this card to work in much shorter connectors. But yeah, we'll play with this another day. Now we know from our investigation two of the what's the emission of two of the pins, and their mission ends and begins and ends in the same connector. They don't leave the connector, and the purpose is to indicate the length of the card. So we can now we have a list, we have a correspondence of how the USB connector maps to PCI Express signals. I think today we don't need to go. We don't need to explore on detail the meaning of all of this. This is an exploration so we can go deeper into elements that we find more interesting. Just to get that out of the way, we have from where the USB was supposed to carry power. This adapter uses those two pins to carry two signals, wake and reset. We can assume that wake has to do with some mechanism to bring computers out of sleep mode. For instance, if we have maybe an Ethernet board plug in a connector, that Ethernet board can bring the PC out of sleep if it receives a combination of signals, and reset is part of the PCI Express protocol. There are a lot of signals in the standard, but I think today is very interesting to discover what's the bare minimum. What are the signals that we basically need for a minimal PCI connection? And those two are apparently, because the connector is using them, those two are part of that minimum. Then we can see that PCI Express has a reference clock coming from the motherboard, and the adapter brings this reference clock to the connector through the USB 2.0 legacy standard data pair. So these pair wires are used to also carry a pair of a signal from a differential pair, which in this case is the reference clock. And as we were kind of anticipating earlier in the visual exploration, the last two groups of signals correspond to the lane, to the single lane that this adapter is going to bring from the PC to our socket over here. And I think we could go a bit deeper on the meaning of this, because initially it could be a bit confusing. We have a total of 4 wires in one side, 4 wires in the other side. But the concept here, according to the PCI Express standard, is that this is bidirectional communication, but each couple, each pair handles communication in one way, in one direction, to put it this way. So the idea is that you have 2 wires, which in this case have differential signals, and one wire is going to carry the positive side of the signal, and the other wire is going to carry the negative side of the signal. And those 2 wires send information in one direction, and then you have another pair of wires, positive and negative again, and going to send information from one direction. So in one case we have the host in one side, and on the other side we have the card, as an example. I'm pretty sure things are more complicated because we're oversimplifying. We have probably a ground reference for each one of them. But the interesting concept here is that a single lane, what in PCI Express lingo is referred as X1, a single lane the data part requires all this. The data part requires a pair that goes in one direction, a pair that goes in the other direction. Each pair obviously is made of two wires, two traces, and some ground plane. So with this in mind, this begins to make, I think, at least for me, it's beginning to make much more sense, because we expect in the USB 3.0 cable, we expect those two pairs to be managing high-speed digital data transmission. To start with, in 3.0, in USB 3.0, through those wires we have 5 gigabits of data in flowing, and more than USB protocols. We have even more. We have even higher the speed. So it makes sense that the 4 wires responsible of carrying the PCI Express lane where the data, with high-speed data is flowing, are using the part of the cable which is responsible to also support high-speed data in USB 3.0. So I think this ties these together, that help us to understand better why the manufacturer of those adapters are reusing these USB components, and we have a better picture of the minimal PCI Express signals that we need to bring a PCI bus out of a computer. And I added some little marks here, just a reminder. This is the beginning of the PCI Express connector. You can go to Wikipedia. You will see that this keeps going. This goes up to 1 lane. So this is what we are, what we are investigating today here. So makes no sense to print all the way to 16, because basically what we find below here after pin 18 of a PCI Express connector is basically an iteration of those 2 pairs. This is the 2 pairs of lane number 1, and then we have the 2 pairs of lane number 2, number 3, number 4, and so forth. This is the beginning of the PCI connector, and here we see the signals that are the bare minimum we need in order for this to work, which I think is very, very interesting. Obviously, this adapter doesn't need to transmit power supply from the motherboard to the connector, because that's handled by external power supply in this case. And we can see here that we get a standard SATA power supply, and all those electronics are here to create the power supply that whatever card we plug here is going to need to follow the standard. So this gives freedom to the manufacturers of this adapter to use all the pins available in the USB connector for signals. And in this case is what we have learned earlier. Just a bit of recap. We have the 2, let's call them present pins, that indicates the length of the card that we're connecting. And we have 2 signals, wake and reset. And we have a reference clock. And we have the 2 pairs that become the first lane of a PCI card. So yeah, that's the mapping of those pins, and let's think about what can we do next. So just a quick detour to do a little test, because I'm working on an idea that is going to be probably destructive. And so just a quick test to show you that that this works. I have the adapter plugged to one of the slots in my PC, I have a kind of old internet adapter plugged to the adapter, and this is the Ethernet connection coming with from the network. Just quick test to prove that this is working, because I'm thinking that from the signals that we have been discovering earlier, we don't have the equipment to deal with with the good stuff. We don't have the equipment today to explore what's happening on those data pairs, the pairs that they're transiting the information coming and going to through the PCI Express port. But there's something interesting. We have a reference clock that, according to the information I could find, this reference clock is not, it doesn't change across PCI Express standard. As you know, there are a number of PCI Express standard. The standard started 20 years ago. There's the version 1, the 2, the 3, the 4, 5, and now they're working in version 7. And every version becomes faster and faster. They usually double the usable information that you can send across those lanes. But the reference clock stays always at 100 megahertz. The reference clock is always 100 megahertz, and that's something we can tackle. That's something we can try to pick and to give it a look. So before I start destroying things, quick test. This is the adapter. It has some fancy lights. Don't get distracted with this. Some voltage indicators, some flashing LEDs. It's all related to the power electronics that this adapter requires to transform the power coming from a SATA adapter to the PCI Express. And we just remove the cable. Network down. Plug it again. And network back up. So this is working. Let's do some distraction. All right. So let me tell you about this little experiment. My goal here is to just intercept one of the wires. I don't know if you can see it here. I soldered SMA coax cable to one of the wires, and I extended the shield of the cable. When this cable, it has a very, very literally paper thin shielding that when you start messing with it goes away. So basically, I extend the shield from one to keep continuity and to give me support for to solder the shield of the coax cable. In the cable I'm interested in, the signal I'm interested in, is one of the wires of the reference clock we saw earlier. According to the USB diagram, this goes through the white and the green pair. We could find it here, and I decided to pick the white to solder. This is very, very, very rough. I know that there is not a lot of science behind this, and that there are proper ways to plug to a differential signal. I know, but it's just an impromptu thing that well, we're exploring. Let's see what we can learn about this. I know that I'm going to miss part of the signal that is going through the other wire, but let's see what we can get. And also we can learn a bit more about this cable. The nice pairs that are twisted around here, and they are with proper independent shielding. They are the high speed pairs that we saw earlier, and that this adapter uses to transmit the high speed PCI Express digital lines. And interestingly, those two wires, they are not really shielded. I guess, maybe for 100 megahertz, it's not necessary in this case, or they didn't have any other option. And we can see here the originally designed cables to transmit power through the legacy USB connector that are used for other purposes in this adapter. But yeah, let's complete the setup with something else. Give me a second. So back to the test setup. We have the same components that we had before. We're just bringing this signal we are improvising, the reference clock, to an SDR module, and we can go into details another day. I'll put the links in the description on about where to get all those components. Basically, this is, you may be familiar with this with more cheaper receivers, but this is a software-defined radio receiver that in this case has capacity enough to handle a 100 megahertz signal. I put DC blocker here just for precaution. It's something I like to do when I'm doing awful things like this one. So yeah, basically the same setup. And the good news is that we have a 100 megahertz signal on the screen. I'm not going to pretend that this is clean in any way. We have a lot of things going on here. We have a lot of reflections. We have signals coming from other places, as you saw earlier. We don't have the SDR receiver is not shielded, but we have a clear 100 megahertz signal on the screen. If I'm going to, you don't see it on the recording, but I'm going to disconnect the cable just to see what's left. Yeah, cable disconnected. So yeah, we have other signals, but and a very faint 100 megahertz, which if you think about it, it makes sense from the point of view that I have next to me my PC is open. My PC has PCI Express ports. All of them have 100 megahertz reference clock. Internally the SDR module is probably also has PCI parts with 100 megahertz. So it makes sense that we have 100 megahertz all over the place. But what I'm trying to prove here is that I'm going to plug it again. Yeah, and we have kind of a strong 100 megahertz signal here. All right. So, just for consistency, we said earlier that this signal is coming from the board, from the motherboard. So if that's true, then all we have here is not really necessary. Let's validate that theory. Let's remove the card. Let's remove the power. And let's go back to the screen. And yeah, we still have the signal. So after successfully getting something out of our PCI Express reference clock connector, something that I find very interesting is that the realization that we have PCI Express in more places that we usually think. A great example is NVMe, and we'll have some sort of NVMe storage at home, and we love it. It's very performant, and yeah, it's part of our daily storage at the moment. And then we have adapters to, if our motherboard doesn't have a way to plug it directly, we can buy adapters, and yeah, they were fine. We have adapters for USB 3.0. We have adapters for USB-C or USB 3.1. We have adapters for Thunderbolt, and we often don't realize that NVMe and PCI Express are very, very, very close related. So close that electrical and a protocol level, they are basically the same. They sell those very inexpensive adapters that basically bring that point home. I think, if I may say that. Here, this adapter basically has the M.2 NVMe connector, and as we can see, it's basically a collection of just mechanical and electrical conversion. We can see how the NVMe connections, they go to our well-known PCI Express connector, and the same for the other side. And as you can see, there are no electronics, absolutely nothing. The only thing we can see is this place where we can inject 12 volts into the PCI Express connector. The NVMe standard just provides 3.3 volts. So most PCI Express cards, they need 12 volts, and we can provide it through those two pins over here. But yeah, this is basically a form factor adapter from NVMe connector M.2 to PCI Express. So we can have some fun with this. Here I have an improved version, which basically those adapters, they have a number of long wires over here, a piece of plastic over there. So they usually are tricky to install in an adapter, because these adapters are designed for very thin and very, 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 very shallow NVMe memory. So I'm using this to have a way to mechanically put this this connector, this adapter in an NVMe socket without, without breaking anything, or without scratching any surface. So next step, I propose to see if that theory is valid. If an NVMe connector is very close related to PCI Express, we should also get 100. We should get the 100 megahertz reference clock from here. So let's see we can make this happen. Let me move the camera. We still have the signal coming from the PC. We need to unplug it. All right, let's be careful. So I'm going to plug the up here. Nothing is happening because we don't have anything connected at the moment in the NVMe adapter. I need the cable. We have now our single lane PC adapter connected to the NVMe connector, the NVMe connector to the NV adapter, and then we can plug it to the USB-C cable. And we have a very similar 100 megahertz spectrum. It's something I've been noticing in this exploration is the shape of the spectrum is not always the same. Different devices have different frequency spectrums, and this relates to something I read about this reference clock, that we can go perhaps deeper another day, but just to leave you with this piece of nugget of information that not all the reference clock across different devices are made equal. So yeah, we have this signal. Let's unplug it. And let's try this other guy. You know what? Let me adjust an option here to see. Yeah, I enable the option hold. It's going to give us more information to help us to compare one spectrum to the other. Let me bring back this adapter. Okay. We have this USB-C reference clock. And now when we disconnect, we have a bit of persistence there in the screen that will help us to compare one with the next one. Yeah, I'm watching using my phone, and that's not very useful. Okay, is it holding? Yes, it's holding. Oh wow, yeah. Very different compared to the other one. Yeah, that confirms my theory. Um, let's go back. The previous adapter. Yeah. I don't know if the camera is yeah, very different. So I apologize for the improvise of the experiment with bad soldering and plugging things into random places, but I think I hope I managed to make sense of the discovery process. I hope we have learned a couple of things about PCI Express. We're still far to get where the interesting things happen, like data transmission lines. But at least we have a way to get PCI Express connectors out of our PCs. We have a way to plug different formats, different adapters, and we dare to to learn about one of the signals, which is the reference clock, and more about this in the future. Thank you, and see you around.